Okay, so if we start with number 16 of the test review, we have composite functions. So we have two equations that we're going to have to try to stick together. So we have f of x equals 2x to the 2/3. And then we have g of x equals 3x to the 1/4. Okay. All right, so the first thing that they want us to do for number 16 is they want us to find f of x over g of x and find the domain. All right, so the first thing we'll do is we'll just dump those two equations on top of each other, and then we'll try to simplify if we can. So f of x is 2x to the 2/3. G of x is 3x to the 1/4. So we go ahead and just divide those just like that. Now the 2 and the 3 we can't simplify any further, but the x's we can because they are the same base. We can go ahead and subtract those exponents. All right, so the 2/3 stays. And then I'm going to pull the x's down here so that we can try to figure out what they simplify to. Now, 2x to the 2/3 divided by x to the 1/4, we have to subtract those exponents. We keep x as the base, but we have to subtract those exponents. Now, the tricky thing about this is we have to get common denominators. Right now, we have a 3 and a 4. We have to get them to be the same in order to subtract. Well, we know that the least common multiple, or the number that 3 and 4 have in common, is 12. So I'm going to multiply this by 3. I'm going to multiply this one by 4. Top and bottom. Okay. So really we end up with x to the 8/12, because 4 times 2 and 4 times 3, minus 3/12. Okay. So I just change these to common denominators. We're going to go ahead and actually subtract this now. So this is really x to the 5/12. 8/12 minus 3/12 is 5/12. So going back up to the equation that we were simplifying, the 2/3 stays the same. These x's, we actually can simplify them to just be x to the 5/12. Okay. All right, and so this is what the actual f of x divided by g of x would be. Now, one thing to look about this, if we are rewriting this as a radical, because this will help us figure out the domain. If we were to rewrite that as a radical, it would actually be the 12th root of 2/3 to the 5th power. Okay? So remember, the number on the bottom of the exponent, when it's a fraction, has to go to be the root. So this is the 12th root of 2/3 to the 5th. Now, one thing to keep in mind about roots, if this is an even number, you cannot have negative numbers in that actual root. Well, 12 is an even number, just like square root. There's a 2 with a square root. Square root is an even number here. We can't have negatives. So the lowest we could actually go, oh, I'm sorry, I missed the variable. This is 2/3 x to the 5th. The lowest we could actually go, since this is an even root, is 0. We can do the square root or the 12th root of 0, but we can't do any negative numbers. So our domain would have to be from 0, including 0, to infinity. Okay? And so again, that was just because this is an even number for the root, we can't have negative values. If this were an odd number, like a 5, a 7, a 9, 11, we can have negatives as well as positives. But for even roots, we can only have 0 and above. So that's why 0 is the lowest we could go for x. And then we could go any number bigger than 0. All right, so if we look at number 17. Now we're going to do f of g of x. So we keep these same equations here at the top, so I won't erase those. But now we're going to do a little bit different of a manipulation with those equations. We're not going to just divide them like we did before. All right, so what we actually have to do now is f of g of x. So we're actually taking this g equation. So this equation right here, we're taking that whole equation and we're actually plugging it into the f equation right where their x is. So the F equation right now is 2 times something, or x, to the 2/3. What we're going to actually put in here is the G equation. Okay. So I just kind of rewrote the F equation, just taking the x out. And what we're going to put in the place for the x is this whole equation. Okay, so keep in mind the 2/3 still stays there. We're just plugging in for x. So I'm going to take this whole thing and put it in here. So this is going to become 3x to the 1/4. Okay, so now we have to try to simplify. Right? The first thing we actually will do is we will deal with this exponent. Okay? So that exponent is going to have to be multiplied by this exponent, and this exponent is going to have to be multiplied by the 3, because technically this is 3 to the 1st. So this 1 that's here also has to get multiplied by that exponent. So to simplify, what we end up with is, I'm going to keep the 2 out in front for right now. It's going to become 3 to the 2/3 x to the 1/4 times 2/3. Okay, so that's 2 times 3 to the 2/3, or 3 to the 2/3 times x, and then for the exponent for x is 1/4 times 2/3. We're going to have to simplify that. All right. So I will keep this the same for right now. So 2 times 3 to the 2/3. But now we can simplify for x. We're going to actually go ahead and multiply these exponents together. We'll get 1 times 2 is just 2. 4 times 3 is 12. Well, 2/12 is actually 1/6. So I'm going to just erase that and just put 1/6. So it's the most simplified form. And that's actually as far as we can go with that, just because we can't simplify 3 to the 2/3. We can't simplify x to the 1/6, that has to stay. So one thing, these guys here, there's some type of number. It doesn't really matter what the number is if we're trying to do the domain. We're just concerned with what this x value is. So if I were to rewrite this using radicals, it would be 2 cube root of 3 squared, which we know is just 9. So I'm going to, now where this came from, I just took this 3 over 2/3. I grabbed the 3 and put that here for the radical. I grabbed the 2 up here, and that stays with the 3 inside. So really this is the cube root of 3 squared. Well, we know 3 squared is just 9. But then we have x to the 1/6. So if I rewrite that using a radical, it's going to be the 6th root of x. Again, this is just some number in front. It doesn't look like the prettiest number to work with. We don't need that number when we're dealing with domain. What we're concerned with is the x value. So this kind of goes back to the question we just did for number 16. This is an even radical. The one we did for number 16 was 12. This one is to the 6th root. Even radicals cannot have negative values for x. So, or can't have negative values under the radical. So we know that the lowest that x can be is 0. So our domain would be just like it was before, 0 to infinity. Right? Again, if this was like an odd number, like to the 5th root or 12th root, we could do all real numbers. We could have negative x's and positive x's, but because this is an even root, we can only have 0 and above. So for 16 and for 17, the domain is just from 0 to infinity. All right, so we'll move to number 18, which deals with transformations. Give me a second to erase all of this. All right, so for 18, you're getting into transformation, so describing how graphs change based off of the numbers that are in the graphs. So reflections, moving it right or left, those are the types of things that we're about to talk about. Okay, so let me write those equations down. So for 18, we have some more kind of composite functions. So let me write down all of the equations. We have f of x equals just the square root of x. So just plain the square root of x. We have g of x equals the cube root. We have g of x equals the cube root. Sorry, that's 3 times. So it's not a cube root, it's actually just a big 3 in front. So 3 square root x minus 4 plus 5 for h of x. We have the cube root of x. And then for p of x, we have negative cube root of x plus 6 minus 7. Okay, so for part A, we have to describe the transformation to create the graph of g of x from f of x. So we have to describe what we need to do to go from this kind of plane equation to this equation. So we want to explain, what do each of these numbers actually do? How does it transform the graph? Well, I'll write out each of them as we kind of go along. So one of the things that happens is we always want to start with the inside of the radical first. So the first thing we'll describe is how the negative 4 changes the graph. So even though this is x minus 4, it actually moves us to the right 4, which is kind of counterintuitive. You would think that minus 4 moves you to the left. It actually moves us to the right. So we're getting moved to the right 4 units. And again, we're just describing how we can change this plane graph into this one. So the first thing we do is we pick this graph up and move it 4 to the right. Okay? Then we want to describe what happens with stretches or shrinks. Numbers on the outside of the radical deal with vertical. So this 3 is a vertical stretch. And it's a vertical stretch by 3. So first we moved it 4 to the right, then we stretched it vertically by 3. And the last thing we'll talk about or describe is what the 5 does. And so the 5 just moves us up 5. If this were a minus, it'd be moving us down. Okay? So just to kind of recap, to go from this plane equation to this one, we moved it to the right 4, then we stretched it vertically by 3, and then we moved it up 5. All right. So that is for part A. For part B, they want us to graph g of x and give the domain and range. Okay, so I'll go through the easiest way to graph it. So I'll come up with the table. I won't actually graph it. I'll kind of do a little sketch of the graph, but I can show you how to come up with the points to graph it. All right, so one thing to keep in mind, the g equation is a square root equation. So we're going to start with the parent function. A parent function is just an equation that's similar to the one that you have that doesn't have any extra numbers kind of thrown in. Because it's the plain Jane kind of equation. So what I'm going to do is I'm going to just look at the square root of x. And I'm going to come up with a table of values just for the square root of x. So if we had plain old square root of x, we can't do negative numbers. We could do 0, we could do 1, and we could do, let's say, 4 and 9. Just because we want to make sure we pick x values that have perfect squares to make our lives a little bit easier when we're plugging things in. So if we were to put in 0 for x, the square root of 0 is just 0. If we were to put in 1 for x, square root of 1 is just 1. If we put in 4 for x, the square root of 4 is 2. And if we put in 9 for x, the square root of 9 is just 3. So these are the kind of the generic points for the parent function. Well, we don't have square root of x. They want us to graph this guy. That's a lot more complicated. We don't just have square root of x. We have 3 times the square root of x minus 4 plus 5. Now, what we actually will do is we'll take these points and we're going to manipulate them. We're going to transform them or move them just like we move the graph. So we described the transformations that we did here. We said we moved it right 4. Well, that deals with the x values. So all of these x values, we need to pick them up and move them 4 to the right. So to do that, we're actually going to add 4 to all of them. Now, just to keep in mind, even though this said minus 4 in the equation, the minus tells us that we're moving to the right, But when we start to change the points, we actually want to add 4, because that's the only way that we can move in the right direction, which is the positive direction. We want to add 4. Okay. If we deal next with the vertical stretch, that means we took the graph and we stretched it. So that means all the y values actually got stretched. So we're going to multiply all these y values by 3. So I'm just going to put parentheses and then 3, meaning we need to multiply all of these y's by 3. Again, we're just kind of taking the parent function and we're transforming it, we're moving it and changing it. And then this last part, we moved it up 5. That deals with the y's. So not only does the stretch deal with the y's, but so does the up part deal with the y. And so if we're moving up, we just need to add 5. Now, it's very important that of the order of how you do this, we want to multiply first and then add. So you always want to multiply first and then add, or subtract if you need to subtract, but multiplication always has to come first. So 0 times 3 is 0, plus 5 is 5. So that's our new y value. 1 times 3 is 3, plus 5 is 8. So that's our new y value for that one. 2 times 3 is 6, plus 5 is 11. That's our new y value there. And then 3 times 3 is 9, plus 5 is 14. So these are all of our new y values. Now our x values, we're just adding 4 to all of the x values. So 4 plus 0 is 4, 4 plus 1 is 5, 4 plus 4 is 8, and 4 plus 9 is 13. Okay? So the way you would actually graph this is you can actually just plot the points 4, 5, 5, 8, 8, 11, and 13, 14. So we took the original, these guys in here, these were the original kind of parent function points, and we transformed them. So now when you transform them, you can just plot the new points. So just to kind of give you an idea what the sketch of the graph would look like, let me shift this over here. It would be a graph. Okay. So the parent function, if we start with that, the parent function, just a regular square root, kind of looks like this. It starts at 0, 0, and then shoots out. But we picked this whole graph up and we moved it to the right, and then we moved it up. So we moved it to the right, 1, 2, 3, 4, and we moved it up, 1, 2, 3, 4, 5. So really, it's starting right here. Instead of starting at 0, 0, it's moved over 4 and up 5. It's actually starting right here. And then it's 3 times taller. So it'd be something really steep, kind of like that. Okay? But to come up with this actual graph, you can definitely just graph those points. And so just to recap, we would do 4, 5 for our point when we graph it, 5, 8, 8, 11, and 13, 14 for our points. Okay? We'll go ahead and do 18 C and D, but it's the exact same way. And so for 18, for part C and D, they want us to compare these two guys, these two cube root equations, and figure out, 1, how we transformed it, and 2, the domain and range. So one thing that I forgot to mention for part B, when we're graphing that new square root function, we want to talk about the domain and range. Well, when we're looking at this, remember for square roots, we can't have negative numbers. So you'd have to ask yourself, what can I put in here that would make this go to 0? Because that would be the lowest value you can have. Well, if we put in 4 for x, 4 minus 4 is 0, that gives us a square root of 0. That's the lowest we could actually do. So for our domain would have to be from 4 to infinity. So we can do 4, 5, 6, 7, 8, 12, 100, a million. We can do anything bigger than 4, but we can't do anything less than 4. Because let's say we put in 3, because 3 is less than 4. 3 minus 4 is a negative number. We can't have negative in the square roots. So for this guy, I'll write it up there. The domain is going to be from 4 to infinity. Okay, bracket for 4, meaning we actually can include 4. We can have the square root of 0, that's fine. We can't have anything less than the square root of 0. And then the range, now this is where you might have to do a little bit of work. The domain goes from the smallest x to the highest x. Okay? The range goes from the smallest y to the highest y. Well, to figure out the range, you can actually use your domain to help you. Whatever the smallest x is, that would give you the smallest y. So if we were to put 4 in for x, we'd get square root of 0, because 4 minus 4 is 0. Well, square root of 0 times 3 would just be 0. plus 5 will be 5. So the lowest y value we'd get is 5, and then we'd go to infinity. So again, the way I did that is I took the lowest x and I plugged it into the equation to figure out what the y value would be at that lowest x point. So when x is 4, the y is actually 5. All right, so if we do the same type of thing with cube root, or with the cube root, so we have, if we first describe the transformation, then what we would have is, we want to start with the inside first. So we went 6 to the left. Even though this is a plus sign, it is actually moving us to the left. It's kind of the opposite. Whereas here where it was minus, it was moving us to the right. So it's moving us to the left. Then we want to start with any multiplication. After we do what's inside the radical, we want to move out to whatever is in front. There is no number actually in front. We just have the negative. So that negative tells us that we actually reflected the graph, or we flipped it over the x-axis. So we flipped it over the x-axis. That's what the negative does. And then the minus 7 is just down 7. So that would be the transformations. Now, if we're coming up with the points to help us graph it, instead of looking at the square root graph, we want to look at just the cube root graph, because these are cube roots that we're dealing with. So I'm going to erase this, and I'm going to come up with the parent function for the cube root. And this is kind of an easier way to graph this, since you likely will not be able to use a calculator, at least for part of the test. Okay. So if we have the cube root of x, okay? Now one thing with cube roots, just like we said before, odd radicals, we can do negatives. Even number radicals, that's where we have a problem, we can't do negatives. But for odd radicals, we can do negatives, that's fine. So when I do my table, I'm just going to pick numbers that are perfect cubes. So I can do negative 8, I can do negative 1, I can do 0, I can do positive 1, and I can do positive 8. So if we were to put in negative 8, the cube root of negative 8 is just negative 2. The cube root of negative 1 is just negative 1. Cube root of 0 is 0. Cube root of positive 1 is 1. And the cube root of 8 is 2. Okay? So these would be the points of just a plain cube root equation. But now we're going to see how we transformed it. Remember, we moved it to the left, we flipped it, and we moved it down. So the next thing we want to do is figure out how can we change these points to graph our new graph. Well, if we moved it to the left 6, that means we need to subtract 6 from all of our x's. Because remember, left is the negative direction. We want to actually subtract 6. So all of these x's, we want to minus 6 from. All right, so the left part deals with the x. Now reflecting us over the y, reflecting us deals with the y values. So all of our y values we want to make negative. So just because this was a negative here, we want to make all of these y values negative. So I'm just going to do parentheses and put a negative in front to remind myself to change the signs. Right? And then we move down 7. So the down part also deals with the y values. Okay? So I'm going to subtract 7. So after I change the signs or multiply by negative 1, I'm going to then subtract 7. Okay? So our new points would be, because remember, these guys in here, these were the old points or the original points. Our new points would end up being negative 6 minus 8. That's negative 14. So I'm just going to write a little table to keep track of our new points. So our new points would be negative 6 minus 8. Well, that's negative 14. And then if we look at the y, negative times a negative 2 makes it a positive 2. And then minus 7 makes it a negative 5. So that's our new point there. Negative 6 minus 1 is negative 7. Negative 1 times negative, or negative times negative 1 is positive 1. Positive 1 minus 7 is negative 6. Okay? Negative 6 minus 0, remember the x's were subtracting 6. So negative 6 minus 0 is negative 6. And then for the y's, 0 times negative 1 is still 0, minus 7 is minus 7. Negative 6 minus 1, because we're subtracting negative 6 from we're subtracting 6 from all of the x values, would be negative 5. And then negative times 1 is negative 1, minus 7 is negative 8. Negative 6 plus 8 would be 2, because we're just subtracting 6 from all of these. All right, and then negative times a positive 2 is negative 2, minus 7 is negative 9. So those would be all of our new points that we would graph. So just to recap, we subtracted 6 from all the x's, the y's we multiplied by negative 1 to reflect it, and then we subtracted 7. So we always do multiplication first, and then we do subtraction or addition second. So these would be the new points that you would apply. Now keep in mind, cube root graphs are easy when it comes to domain and range, because cube root graphs have all real numbers for domain and range, because we can do negatives and we can do positives, or we can do fractions. Cube root, and the same is true for any odd radical, whether it's the 5th root or 7th root, you have no restrictions. So you can do positives, negatives, doesn't matter. So if you were to graph this, it would look something like, now the normal cube root graph would look like this. It would go through the origin. Well, our graph has been moved to the left 6, and it has been moved down, and it's been flipped. So if we move it to the left first, it would come over this way. So 1, 2, 3, 4, 5, 6. So instead of it being at 0, 0 where it crosses over, it's going to cross over here, 6 to the left. And then we would flip it, so instead of kind of coming up this way, it's going to be falling down. And then we would also be moved down 7 units. So more than likely, this graph would look something like this. And actually, to be a little more accurate, but you have the points that you could definitely graph to make sure you have the accurate graph of it. But I'm just trying to show you kind of a sketch of what it would look like. Is more than likely it would look something like this, where instead of being at 0, 0, we moved over 6, we moved down 7, and then it's flipped. So instead of kind of rising, it's actually falling. But you can definitely just plot those points to figure out exactly what that graph would look like. Now for domain and range of cube functions, domain would be all real numbers. So from negative infinity to infinity, the range would also be all real numbers. Okay? We're not limited for cube roots. All real numbers for domain and range. All right, so we just have a few more. All right, so number 19. All right, this is you'd have to use a calculator for. So for part A, you would just take that equation that they gave you, you'd put it in the calculator. Now, one thing to note, when you put it in the calculator, your calculator is not going to have t, it's going to have x. So you would just enter it in with an x instead of a t. So you would enter it in as 1.78 times the square root of x minus 0.3 plus 62.7. And then what you do, so part B kind of walks you through exactly how you would solve it. So I'll kind of explain part B of how you would actually put it in the calculator. And I'm talking about number 19. So generally for word problems, they would give you the equation. It's just up to you to be able to solve the equation for whatever they want you to look for. So the equation they give you is 1.78 square root of x minus 0.3 plus 62.7. Okay. And this equation is supposed to model age, the age to which a U.S. newborn could expect to live. So for part B, they want you to find what birth year would an infant expect to live at least 75.7 years. Well, in that case, we want to know when this whole equation would be equal to 75.7. So what you would actually do, and they want you to use your calculator to do this, you would put this into y1 to graph it. You would put this into y2 to graph it, and they want you to find where they intersect. So there's a button that says trace on your calculator towards the top. you'd want to click that button, and then I think it's the fourth or fifth option allows you to do intersect, and you'd find where these two equations actually meet. So what will happen when you graph it is you'll graph on one coordinate plane. You'll have this graph, which will look something like, let's say this. And then you also will have this graph, which will be something like, let's say this, some type of line, okay? What you want to find, and it won't look exactly like this, but this is as an example. What you will find when you graph both of these, you'll find they intersect, and that's what you want to find is where they intersect. And what the calculator will give you, that exact point. Now what we want is we want just the x value of that point. So let's say they give you, when you find that intersection, hypothetically speaking, let's say the intersection says that this x value is 23.1. Again, just kind of hypothetically speaking, if that's the x value. What we want to then do is take that x value and add it to 1940, because they told us that the equation started in 1940. So we would just take 1940 and add whatever that x value is that the calculator tells you where those two equations intersect. So if it intersects at 23.1, we can just round that to the nearest whole number, which would be 23. So a child born in 1963 could expect to live to be 75.7. So again, this is kind of, these numbers aren't going to be correct. I just kind of made this up as an example. But you would graph this equation that they gave you. You'd graph the 75.7 in y2. Your graph would look something like this, where you have a curve and then you have a line. You want to allow the calculator, have the calculator using the trace button, find where those two lines intersect. You're going to take the x value that the calculator gives you, and you're going to add that to 1940 so that you could find the exact year. Because this equation starts in 1940. So when x is 0, that's 1940. Well, if x is 23, that's 23 years after 1940. So the answer should actually be, 1963, 1975, 19 something. We want to find that actual year. Right? So then we'll finish up with number 20. And for number 20, we're just solving for the variable. Okay, so just give me a second to erase the board. All right. Let me erase this part too, so we'll have more space. All right, so for part A, we have the square root of 3n plus 13 minus n equals 5. Okay, so one thing to note, the n is not actually in the radical, which is fine. But before we do any types of problems like this, we want to make sure the radical is by itself. So anything that's being added or subtracted or multiplied, we want to move it over to the other side. So I'm just going to add the n over. So we get square root of 3n plus 13 equals 5 plus n, or n plus 5. All right, and then at that point, if we want to get this n out of the radical, we have to square it both sides. So on the left, we end up with 3n plus 13. That just comes out of the radical. But this we have to FOIL out. We're not just going to square the 5 and square the n. We actually have to FOIL it out as if it were 5 plus n times another 5 plus n. Okay? So take a minute to do that, FOIL it out, and I'll try to kind of walk through the steps too. Okay. So when we FOIL it, we actually get 25. 5 times 5 will be 25. N times 5 is 5n, but we have another 5 times n, which is another 5n, so we have 10 n's total, plus n times n is n squared. So 3n plus 13 equals 25 plus 10n plus n squared. We want to solve for n, so we're going to have to get everything onto one side and probably set ourselves up to factor. So what we would do then is, I'm just going to move all this over to that side. So I'm going to subtract 3n, and I'm going to subtract 13. So what we're left with then is 0 equals n squared. 10n minus 3n is just plus 7n. 25 minus 13 is positive 12. Okay, now we want to factor. Now keep in mind, we want to figure out what could multiply to 12, but add to get us 7. Well, that would be 3 and 4. So 3 times 4 is 12, and 3 plus 4 is 7. So these would need to be n plus 4 times n plus 3. Okay, this equals 0. So we technically then set each of these pieces equal to 0. Okay, we'll subtract 3. So we would get n is equal to negative 3 minus 4. Here we get n equals negative 4. Okay, now it's very important for these problems to definitely check your solutions, because one or both may not work. If a solution does not work, it's called extraneous, but you have to check to see if it actually works. So I'll do it for this exercise, but for the other two that we'll do, I'll leave it up to you to check your work to make sure that they actually work out. So we can go all the way back to the original, and we're just plugging in negative 4, making sure it works, and then we'll plug in negative 3 to make sure that also works. So if we were to plug in negative 4 into the top equation, into what we started with, it would be the square root of 3 times negative 4 plus 13 minus negative 4 equals 5. Okay? And we want to see, does it really actually equal 5? All right, so 3 times negative 4, that's negative 12 plus 13. So negative 12 plus 13, that's just 1. Well, the square root of 1 is just 1. So all of this right here actually simplifies to just be 1. Minus a negative is actually plus. And 1 plus 4 does actually equal 5. So this actually did work out. So negative 4 right now actually works out as a solution. Okay, we would do the exact same thing trying negative 3. And if it doesn't work, it's fine. It just means that it's not a solution. It's an extraneous solution. And if you were to do a problem like this and let's say both of them don't work out, then you just say that there's no solution. All right. So we would do it for also negative 3. So it'd be 3 times negative 3 plus 13 minus negative 3. We want to see if that actually equals 5. So we would get negative 3 times 3 is negative 9. Negative 9 plus 3 is square root of 4. Minus a negative is really just plus. Well, square root of 4 is just 2. So 2 plus 3 actually does equal 5. So they both actually worked. So both negative 4 and negative 3 would be solutions to that original problem we started with. Okay. So 2 more. Let me erase this, and I'll write both of them down, and we'll tackle them. So just remember, for these problems that I'm about to do, I won't actually go through the last step of checking, but just make sure that you practice checking your work, just because some of those solutions may or may not work, and you won't really know for sure unless you take those solutions and plug them back in to the original equation. Okay, so I'm going to write them both down, and we'll just tackle them one at a time. Okay, so we start with this one first. Start with this one first. Okay, so this guy is raised to the 2/5 power. Whatever is raised to the exponent, we want to isolate everything away from it first before we tackle the actual parentheses here. So first I'm going to add the 8 over. So we're going to get 3x minus 7 to the 2/5. So we would get 3x minus 7 to the 2/5 equals 12, because 8 plus 4 is 12. Then we would go ahead and divide by 3. So we'd get x minus 7 to the 2/5 equals 4. Okay. Now we can go ahead and actually tackle this exponent. So if we have something raised to an exponent, we want to get rid of the exponent, we actually have to raise both sides to the reciprocal of the exponent, or the fraction but flipped. So if this is x minus 7 to the 2/5, we're actually going to raise both sides to the 5/2 power. So we're going to raise this to the 5 over 2, and we're going to have to raise this to the 5 over 2. Okay? The good thing about that is these exponents would cancel each other out. So on the left, we're left with just x minus 7 equals 4 to the 5/2 power. Okay? Now we want to simplify 4 to the 5/2 power, assuming that you don't get to use a calculator. Remember, if we have fractional exponents, we can use our little trick. So I'm just going to rewrite this as keep the 5/2, but I'm going to grab the 2, put the 2 in here. Well, we know 4 is 2 squared. Well, this is technically 2 over 1, so this 2 and that 2 actually cancel. So we're left with 2 to the 5th on the right side. So really 4 to the 5/2 is actually the same as 2 to the 5th, which is 32. We still have x minus 7 on the left. We can go ahead and actually just add 7 to both sides. So we get x equals 39 for the final answer. So just to briefly recap, I took the denominator of this fractional exponent, put it inside, figured out that 2 squared was actually equal to 4. Those 2's canceled. We left with 2 to the 5th. 2 to the 5th is actually 32. We go ahead and we added the 7. So x equals 39. Now remember, you'd want to take this back and plug it back into the original just to make sure it worked. Okay? So then if we tackle the very final problem of your review, is this guy. So we have square roots on both sides, and then we have the number 3 on the right. The easiest way actually to do this would be to move one of the radicals over. It doesn't matter what square root we move, but we want to move one of the square roots over before we square it. Just because if we square it the way that it is now to try to get rid of the radical, we're going to be left with radicals, and our whole goal is to try to get rid of the radicals. So the first thing I'm just going to do is I'm going to move this one over to the other side. So we would end up with the square root of y plus 1 equals 3 minus the square root of y minus 2. So again, this was being added, so I just subtracted this whole radical over to the other side. Right? Now what we can do is we can square it to get rid of the radical. Okay, so let's start with this side first. The square root of 1 plus 1 of y plus 1 squared just becomes y plus 1. But this guy actually has to be FOILed out. So even though this is squared, really what we have is 3 minus square root of y minus 2 times another 1. So we're going to do 3 times 3, which is 9. 3 times negative square root of y minus 2 is just going to be negative 3 square root of y minus 2. Just dump the 3 in front. Okay. And then this 3 times negative square root of y minus 2 would just be minus another minus 3y minus 2. And then lastly, these two guys multiplied together, their radicals would just be a minus times a minus is a plus. Square root times that square root, the square root goes away, and we just get y minus 2. Okay, so to try to simplify what we have, we would then end up having to combine like terms. So one thing that I noticed is that our y's will actually disappear, just because we have one y here and one y here. So if we were to subtract them, they're going to actually cross out. So at least we're kind of simplifying some of our work here. The 9 and the minus 2, we can combine together to just be 7. These guys, minus 3 square root y minus 2 and another minus 3 square root y minus 2, we can combine to just be minus 6 square roots of y minus 2, right, equals 1. So the y's again canceled. If we were to subtract them, they'd go away. I combine these two together to get this one. And then the 9 and the negative 2, I combine together to make 7. Okay. From there, what I'm going to do, I'm just going to subtract 7 over, because I'm trying to isolate the radical so that we can square it to get rid of it, hopefully. So anything that's on the side with the square root, I'm just moving over to the other side. So if I subtract it over, I get negative 6 equals negative 6 square root of y minus 2. Okay. And then I'm going to just divide both sides by negative 6. So this becomes a 1 on the left equals just square root of y minus 2, because those cancel. And now we're setting ourselves up pretty nicely to just square and kind of be done with the y and figure out what y is equal to. So we can just square both sides. So 1 squared is just 1. And then the square root of y minus 2 squared is just y minus 2. So then we can just go ahead and add 2. So I'll finish it over here. So we get y equals 3. And of course, you'd always want to go back, all the way back up to our original, which is here, and you'd want to plug in 3 just to make sure it actually works. Since 3 was the only answer that we got, if 3 actually does not work, it means there's no solution to this particular problem. Okay? So just to kind of recap what we did, I moved this radical over to the other side. We squared both sides, but remember, when we squared this, we had to actually FOIL it out. So that's what all this work was actually FOILing it out. We simplified as much as we could. The good thing is the y here and the y here actually canceled out. And then we combined the negative 2 and the 9 together. We combined these guys together. And then we got to this step. And then we just wanted to isolate the radical. So I moved everything over that didn't have anything to do with the square root. We subtracted the 7 first. Then we divided by negative 6. Then we were left with 1 equals the square root of y minus 2. And then we just squared both sides. So that we ended up with just 1 equals y minus 2. We go ahead and we added the 2's. So we got y equals 3. And again, you just want to double check into the original problem to make sure it actually does work out. So hopefully this was helpful. This went over the whole test review for Unit 5.